My name is Cameron Dyer, and I'm going to talk to you about selection and Hardy-Weinberg equilibrium in population genetics. First, we're going to examine a population and prove that the population is in equilibrium, and then we're going to examine the same population after stabilizing selection has taken place. This population of horses lives in a valley where no other horses are able to reach them. We can see that we have three different phenotypes, red, blue, and purple, and three different genotypes. To satisfy Hardy-Weinberg equilibrium, we have to meet these assumptions. Our population of horses satisfy these criteria, so we move on and can conclude that at equilibrium, the genotypic frequencies are in the proportion listed here. Let's do some calculations to ensure that this is true. To find the frequency of the big A allele, we'll take 2 alleles each from our 8 red individuals and add to it 24 big A alleles from our heterozygotes, then divide by the total number of alleles, which is 2 times 50 or 100. That gives us a frequency of 0.4. We then do the same thing for the little A allele to get a frequency of 0.6. Great. Now let's plug those numbers into the prediction from the Hardy-Weinberg equilibrium. Our total equals 1, so we can state that our population is in equilibrium. These numbers indicate our population's genotypic frequency. Therefore, this is our genotypic array. Now let's consider the same population, except now the green fields they live in have become purple due to climate change. The heterozygous genotype has an advantage over the other two genotypes. The purple horses blend in with the fields, so are less likely to be predated by the horse's natural predator, giant frogs. If the purple horse now has a better ability to survive and reproduce, we say it has better fitness, and if the purple horse is more fit, we know that selection is taking place. We are no longer able to assume that no selection is taking place, so we don't meet the top criteria. Therefore, our population is no longer in equilibrium. Let's see what effect selection has on our calculations. Here's our original population data, but now let's use our initial frequency values instead of the number of individuals observed. And now let's include our fitness values. These values indicate how likely each genotype is to survive and reproduce. For a population in equilibrium, the fitness value is 1. After selection, we know that our purple horses are going to thrive, so their fitness values are 1.2. The blue horses seem to match the purple fields a bit better than the red horses, so the blue have a fitness value higher than the red. We can calculate the proportion of how much of each genotype we will see in this population by multiplying the initial frequency by their fitness. This value is called the unadjusted survivors, which we then sum up to find the average fitness of the population after selection. Now we need to divide our unadjusted survivors total by the average fitness of the population. This gives us our relative frequencies of each genotype after selection occurs. This means that our new genotypic array will be this. Finally, we can calculate the frequencies of the alleles by adding the frequency of the homozygous genotype to half of the frequency of the heterozygous and get 0.41122 and 0.58879. This is how often we will see the big A and little a allele appear in the population, respectively. But what kind of selection is occurring? For this, let's look at our initial and final genotypic arrays side by side. We can see that our population of red and blue horses will drop after selection and that our population of purple horses will rise. This means that this is stabilizing selection, and over time the population of red and blue horses will continue to drop while the population of purple horses grows. However, because the purple horses are heterozygotes, both alleles will still remain in the population.